What if the secret to sustainable artificial intelligence isn't found in writing more code, but in understanding the physical limits of the machines running it? As we race toward a future where AI touches every corner of our lives, from the electricity powering our homes to the language we use to describe our world, a hidden revolution is taking place inside the very chips that drive these technologies. Today, we are diving deep into a collection of groundbreaking research that reveals how the next generation of AI is being built not just on algorithms, but on a fundamental rethinking of energy, resilience, and efficiency. Stay until the end because the findings we uncover today challenge everything we thought we knew about how intelligent systems should be designed, proving that the path forward requires a delicate balance between raw power and subtle precision. For years, the narrative surrounding artificial intelligence has been dominated by the sheer scale of computation. We marvel at models that can write poetry, diagnose diseases, and predict weather patterns with uncanny accuracy. However, beneath this surface of rapid advancement lies a growing crisis of sustainability and fragility. As models become larger and more complex, the energy required to train them has skyrocketed, often outlining a carbon footprint that contradicts our global climate goals. Furthermore, our reliance on these systems has exposed a critical vulnerability. When things go wrong, recovery is often slow and brittle, dependent on heavy-handed interventions that disrupt service. At the same time, the push to make AI accessible on everyday devices has hit a wall of inefficiency, where the sheer weight of high-precision data slows down innovation and drains batteries. The core problem is that we have been optimizing for performance in isolation, ignoring the intricate web of hardware constraints, energy scaling laws, and the need for robust fault tolerance that keeps these systems running in the real world. Without addressing these foundational issues, we risk building a digital empire on shaky ground, one that is too energy-intensive to sustain and too fragile to trust with our most critical infrastructure. But now, a new wave of research is turning the tide, offering a blueprint for a more balanced and resilient AI ecosystem. Imagine a model that treats the training of neural networks like an architectural blueprint, decomposing the energy consumption into distinct layers of compute, memory traffic, and a novel speed-up factor. This roofline-inspired approach allows us to see clearly how different hardware configurations impact energy use, moving us away from vague carbon footprints toward precise, actionable scaling laws. In parallel, a new framework named Concordia is redefining what it means to be fault-tolerant. Instead of relying on slow, CPU-side checks that can bottleneck a system, Concordia introduces a persistent kernel that lives directly on the GPU. This shift is revolutionary. It allows the system to restore service in just 1.5 seconds after a failure, operating nearly 220 times faster than traditional methods. It is like replacing a slow, manual reboot with an instant, automatic healing mechanism that happens invisibly in the background. The story of efficiency continues with breakthroughs in how we handle data itself. Researchers have introduced GRINC and HyperQuant, two approaches that are shattering the limitations of data compression. GRINC acts like a dynamic prism, adjusting the precision of information in real-time based importance, enabling effective 2-bit generation without losing accuracy. Meanwhile, HyperQuant achieves a compression rate nearly 4 times better for linear weights by integrating mathematical transforms with optimal lattices. Think of it as packing a suitcase. Instead of stuffing it full of heavy, high-precision files that weigh you down, these new methods fold the data intelligently, fitting more value into less space. This is not just about saving storage. It is about unlocking the potential of AI on edge devices, from smartphones to remote sensors, by eliminating the inefficiency of carrying unnecessary data baggage. These technical leaps extend far beyond the chip, reshaping how we communicate and apply intelligence in our daily lives. We are seeing a shift where AI moves from being a black box to a transparent partner. New frameworks are emerging that unite diverse optimization strategies, revealing that under-adopted techniques often outperform our current defaults. In the realm of language, studies are uncovering how the metaphors we choose to describe science, like framing research as a war, can subtly erode credibility and influence funding, challenging us to be more mindful of our narrative choices. Moreover, AI is learning to mimic human cognition in profound ways. Investigations into prospective memory show that while AI struggles with spontaneous, proactive intervention compared to human retrospection, new protocols are being established to measure and improve this autonomy. From classifying plant diseases with unprecedented accuracy by dynamically routing inputs across different expert models, to forecasting electricity loads by explicitly modeling the nonlinear relationship between human mobility and power usage, the applications are limitless. Even the way we evaluate these systems is changing. We are moving from generic post hoc metrics to goal-driven specifications derived directly from source code, ensuring that we measure what truly matters. Perhaps most strikingly, the integration of knowledge graphs with language models is allowing AI to detect and repair semantic faults with over 90% accuracy, grounding digital corrections in physical reality. So, what does all this mean for the future of intelligence? It signifies a maturation of the field. We are moving past the initial hype of raw computational power